So what's up mga ka-Chets? Kuya Dale here. So I'm back with another Chet Calc lesson, and today we're gonna discuss about mole and molecular weight. So I know there's some of you, including me, that is really confused about this particular topic. So I'm here to help you. Let's get right into our lesson. So here it is, our lesson for today. So it's mole and molecular weight. So this is under the chemical engineering calculations topic, and you will encounter this in your second year. So let's define some terms first. So when we talk about mole, so it's a certain amount of material corresponding to a specified number of molecules, atoms, electrons, or other specified types of particles. So it's really a special unit, guys. So it's been created to quantify large amount of things. Okay, so we have two types of moles in the SI and in the English unit, but basically they just mean the same thing, but the way they are obtained is different. Okay, so when we say gram mole, it is the SI unit. So it is the SI unit, which is composed of 6.022 times 10 to the 23rd. Then it is called the Avogadro's number molecules. Okay, so if you can't memorize this, it is in your calculator, especially if your calculator is Casio. So it's in press the shift and shift 7 and then enter 24. So you will see the Avogadro's number like this. So it's Na, and then it has the value of 6.0221 times 10 to the 23. Okay, and then if you are talking about pound mole, just basically the same thing, but it's from the SI unit, which is the gram mole. So you multiply it with 453.6 or 454. Okay, so either of the two. And then molecular weight is the mass per mole. So mass per mole. So typically the units here is grams per mole. So basically, if you say that what is the weight of one mole of that substance. For example, if you have a 1 mole of carbon 12 atoms, so 1 mole of the 1 mole of carbon atoms weighs 12.01 grams. So that's basically just it. So 1 mole of its atoms weighs 12.01 grams. Okay, so and 1 mole is this. And then average molecular weight, pseudo molecular weight computed by dividing the mass in a mixture or solution by the number of moles in the mixture or solution. So this is really this is important in chemical engineering calculations. So we have a mixture of substance, for example air, so you don't have the definite molecular weight of air, so we get its average. Okay, so it will be discussed in the later, so we have examples of that. Okay, so let's move on. And in your Paris, so I put here the tables that we will be using. So basically, it's just one table, the table 1-17 in your 8th edition. And then the most important conversion that we will be using here is the 1 pound mole is equal to 453.59 gram moles. Okay, so you won't memorize, if you can't memorize the 454 gram moles is to 1 pound mole, so you can find it in your pairs. Okay, so let's get into a sample problem. Alright, so if a bucket holds 2 pounds of sodium hydroxide, so how many pound moles of NaO or sodium hydroxide does it contain, and then how many gram moles of NaO does it contain? Okay, so there are two different things. So pound mole, so first we are being required of uh, pound moles, and then the second are being required to solve for gram moles. Okay, and then for the second item, we are asked how many pounds of sodium hydroxide are in 7.5 gram moles of NaO. Okay, so let's get right into it. So letter A, you solve that. So two 2 pounds of NaO. What is the molecular weight of sodium hydroxide? So 23, sodium is 23, oxygen is 16, plus 1 plus 40, right? 40 pounds. So if you can't memorize this, if you don't know, you can always look at the periodic table in your Paris, or if you have a separate periodic table in hand. Pound mole NaO, and this is equal to 0.05 pound mole NaO. Okay, that's it. That's the answer. In the second part, so we will now have to use, if you are like me, you can convert these pounds to kilograms and then to grams. So it takes a long time. So that's how I solve it. But if you are using the 454 gram moles per pound mole, so it will be easier. So, but if you can't remember it, so you can use this. So later we will be using that. So this is a familiar conversion to you. So this is how I memorize it. So 1 kilogram is equal to 2.20462 pounds. And then 1,000 grams is in 1 kilogram. And then we have our gram mole of NaO over, we have 40 grams, okay, 40 grams, and it is equal to 22.7 gram moles. Okay, so actually don't be confused. So there are books that just put mole, and then there are gram moles. So they're just basically the same thing. It indicates that the mole was derived from the grams. Okay, so for example, the pound moles or the Lb-Mol, it signifies that it was derived from the pound. Okay, so that's really the caveat there. So don't worry about that. They're just there to confuse you, but it signifies something. Okay, so let's move on to the second part. So we have 7.5 gram mole of NaO, and then we have to find the pounds, right? So we have to convert this to pound moles. So 454 gram moles NaO. and is in pound mole NaO. And 40 pounds of NaO is to 1 pound mole of NaO. Okay, so cancel the units, cancel. So you're now left with pounds of NaO. So we have 0.661 pounds of sodium hydroxide. Okay, so let's move on. Example. So calculate the average molecular weight of air. So assuming that air is 21% oxygen and then 79% nitrogen. Okay, so I have discussed this um, in the chemistry in the atmosphere, the lesson. If you haven't seen it, so make sure to watch it. I'll post a link in the upper right hand corner of the screen so you can watch it. Okay, so how do we calculate the average molecular weight of air? So I discussed this earlier, and then we will go in depth on this right now. Okay, so always, so there is a rule here. Okay, so if you are given the percentage of this, so if you are given a percentage of something, always there are two bases that you can solve this. Okay, so you have the molar basis and then you have the mass basis, but how do you distinguish from the two, or what will you use? So if you are given the gas, so if you are given a gas percentages, so for example here we are given 21% and 17%, but we don't know what it is, if it is molar basis and then if it is mass basis. So if it is gas, always assume that it is molar basis. Okay, and if it is liquid or solid, solid or liquid, so assume that it is on a mass basis. Okay, so here we are given the percentages of gases here, but we don't know. So but we know that oxygen and nitrogen are gases. So we will use the molar basis now. Okay, so molar basis. So how do we calculate the average molecular weight of air? It's just simple, guys. So we have to have a basis of 1 gram mole of air. Okay, 1 gram mole of air. So 1 gram mole of air. So what are the molecular weights of oxygen and nitrogen? So we are given here. So if you look at your periodic table, so if the molecular weight of oxygen, the diatomic oxygen, is 32 grams per mole. Okay, and then we will multiply it by its molar percentage. Okay, so 0.21. So just put here molecular weight of air. So here, and then what is the molecular weight of nitrogen, the atomic nitrogen? It is 28.2 grams per mole. Then multiply it by its molar percentage. Okay, and then you will get 20 9.0 grams of uh, sorry, so grams per mole air. Okay, so that's it. That's how simple it is to calculate the average molecular weight of air. Okay, next, let's talk about mole fraction. So mole fraction is simply the number of moles of a particular substance in a mixture or solution divided by the total number of moles present in the mixture or solution. This definition holds for gases, liquids, and solids. So what I have said earlier, so gas, if you are given the gas, always assume the mole percentage or mole fraction. And if you are given a liquid or solid, uh, assume weight percentage or weight fraction. Okay, so let's move on. So in the fourth problem, so we are asked of the weight fraction and the mole fraction of each component in the drain cleaner. So industrial strength drain cleaner contains 5 kilograms of water and 5 kilograms of sodium hydroxide. What are the mass, the weight fraction, and the mole fraction of each component in the drain cleaner? Okay, so we will make a table for you so that it will be easy to be understood. Okay, so first is the column of the component. Sorry, component, and then the kilograms, and then the weight fraction, the molecular weight, and then the kilogram moles, and the mole fraction. Okay, so mole fraction is ml. Okay, so we have our water and then our sodium hydroxide. So it is equal. So 5 kilograms and 5 kilograms also. So if we get their weight fraction, so we have to total this first. So we have 10 kilograms total. So if we want to get the weight fraction of these, so just divide the weight of water by its total weight. Okay, so 5 divided by 10 is 0.5, and also 5 divided by 10 is 0.5. So they are equal in weight fractions. So if you if you sum this, you have 1. Then we have to get their molecular weight. So water, if you get its molecular weight, so it's approximately 18, and then the sodium hydroxide is 40. So now you have to divide. So we have to divide. So we have to get the kilogram moles of our components. So to get this, we have to divide our weight with our molecular weight. Okay, so it's 5 divided by 18. Then we get our kilogram moles. So 5 divided by 18, so we have 278. And then 5 divided by 40, it's 0.125. If you add this, you will get 0.043. Okay, and then if you want to get, we are asked to get the mole fraction. So just divide 0.278 by 0.403 to get the mole fraction of water. Okay, so it's 0.69, and then here the answer is 0.31. Then if you add it, just 1. So okay, so we now have our answers. So our weight fraction or mass fraction is 0.5 and 0.5, and then our mole fractions are 0.69 and 0.31. All right. So that's it. Then we move on to another example. So a solid compound was found to contain 42.11 grams 42.11% carbon, and then 51.46% oxygen, and 6.43% H. So its molecular weight was about 341. What is the formula for the compound? So if you remember, uh, in your general chemistry, so if you are given the percentages of the elements, okay, percentages of elements, you have to assume that it is in weight basis, okay, weight basis. If you are given the percentages of each element and COH, okay, so we have to assume, and then we are given the uh, molecular weight of the compound, and we are asked for the formula of the compound. Okay, so the first step is we will get the empirical formula first, and then we will get the molecular formula. Okay, so let's begin. So how do we get this? So we have to have a basis. Okay, so I told you that the basis was to be in weight basis. So our basis is 100 grams of compound. So it's easier that way. Because the weight of the elements is just the numbers of the percentages. Okay, so if we multiply this by that, so we will get the percentage, the weight of the element. So we will put here C and H and O. CHO. So the weight of the individual atoms is 42.11, and then 6.43, and then 51.46 grams. Okay, so we will now get their moles. Okay, so we will get their moles so that we will know their molar ratio. Okay, so we'll get their moles. So we just have to divide them by their molar weight, so molecular weight. Okay, so carbon, so it has a molecular weight of 12. Okay, so 12. Just divide it, and then hydrogen is just 1, and then our oxygen is 16. So we'll now get their moles, number of moles. So we have 3.51, and then 6.43, and 3.21. Okay, so now what will we do next? So remember that to get the ratio of these elements, we have to multiply them by the lowest number of moles in the group of elements. So the lowest number of moles among the three elements is oxygen. Okay, so we'll have to multiply it by 3.21. All of them, we have to divide them by 3.21 so that we have a basis now of we'll get the ratio of each element in the compound. So we have the oxygen, we have 1, and then the hydrogen, we have approximately 2, and then our carbon is 1.09. So if you think we'll have to stop here, so it's actually not the case. So we'll have to find a multiplier so that all of them will have the whole numbers in the subscripts. So we now have our um, we now have these H2 then O. Okay, so C1.09 H2 and O. Okay, so if you will get the um, molecular weight of this empirical formula. So this is the empirical formula. We will get around 30 grams per mole. And then we will divide that with we were given the molecular weight of the compound, right? So we'll divide that by 30 so that we will get the number of the true number of these elements in the compound. Okay, so we just represent that by 10, and then 341 divided by 30. Now this is around 11 11.4 something, 11.4. And then we just if we can neglect the 11.4 there, just we will multiply it by the numbers below, so in the subscripts. So we will have, so C 1.09 times 11, we have 12 times 12, and then now we'll have a 12 in the C, and then H will be 22, and then O will be 11. Okay, so if you multiply that 11 by these numbers, you will get these. And then if you can notice, if you will notice, this is our sucrose or our table sugar. Okay, so that's how you get that. Second to the last example. So example has a specific volume of 5.2 cubic meters per kilogram and a molar volume of 1,160 cubic meters per kilogram mole. So determine the molecular weight of the material. So we will have to determine the molecular weight of the material. So we are asked by this molecular weight, and we are only given two values, so we will use them. Okay, so I've taught you about dimensional consistency. So what will be the order, or what will be the divisor and the dividend here, so that we will get the desired units, which is kilograms per kilogram mole. So that's our desired unit. Okay, so we will have to not actually experiment, but we know that 1,160 already has the kilogram mole in the denominator. Okay, so we'll put it in the numerator so that the kilogram mole is in the denominator. Okay, and then we'll have to divide that. So put a large bar here. We'll divide that by 5.2 cubic meters per kilogram. And then if you can see that if you proceed the operation, you can see, so the divisor now will be we will get now the reciprocal of the divisor, right? So the kilogram is on the numerator now, and then 5.2 cubic meters. So we'll have to cancel our cubic meters, and then we'll get the final answer, 21 point no, no. 223.08 kilogram per kilogram mole. Okay, so now that's the answer of that. So it's really easy. Okay, so if you don't get this, you can ask me in the comments below, or you can message me in my FB account. Okay, so last example. So this is actually simple, a simple example. So I have shown you this, how to calculate this already. So you have a 100 kilograms of gas in the following composition. Okay, we have methane, CH4, methane, we have 30%, then the hydrogen, we have 10%, then N2, 60%. What is the average molecular weight of this gas? So I have told you earlier, if you are given this, you have to get its molar. So these are gases, right? So you can't weigh gases. So muna. That's why you can go with the weight of gases as basis on your calculations. So we'll now use the molar basis here. Okay, so molar base of this. So actually pretty simple. Okay, so the molecular weight of our methane is, so we have the gas. Okay, so the molecular weight of our methane is 16.05 grams per mole, and then we will multiply that by its molar percentage. Okay, molar fraction, and then the hydrogen is 2.02 grams per mole, 0.10. Okay, so it's molar fraction, and then the N2 is 28.013 grams per mole, then multiply it by 0.6. So we'll now have the average molecular weight of this gas as 21.82 grams per mole. Okay, so it's that easy. Guys. So if you don't get it, just ask me in the comments below. Okay, so I will give you practice problems. Okay, so you can answer it in the comments below, or you can PM me in my FB account. Okay, so we have to convert the following. So we have this here we have our I have something for you to convert and then to analyze. So average molecular weight of the gas. So I've shown you how to calculate this, and then also the last practice problem I will give you is this. Okay, average molecular weight of this gas in American engineering system of units, meaning you have to the units for this will be pound per pound mole. That's it. Okay, pound per pound mole. The final answer will have the units of pound per pound mole. Okay, so that's it. So if you have any questions, you know where to find me. So here is my Facebook name, and then you can ask me also in the comments below. Okay, so the book that I am using is the same. It's G-Mol and Riggs, the basic principles and calculations in chemical engineering. Okay, so that's it. It's really simple topic, and I hope you can get it. Okay, so it's really important that you will understand this, because um, calculations in chemical engineering. So actually, I am preparing you for something bigger. So I hope you can get this. I hope you are not confused by this. Okay. So that's it. Please like and subscribe for this video, and then share this to other persons that might need these videos so that we can help them. Okay. So that's it. Bye bye. That's it. Bye bye. See you in the next video.